So, as we think about limit, we are looking at what y is doing when they have given us some parameters on x. And the first thing we need to think about is what direction are we coming from? You can have specific limits from specific directions. And so, this first one that we're going to talk about is our left-handed limit. Now, what this means with a left-handed limit is that if you start traveling from the left or the negative side of the graph towards the x value that they've given you, what is y doing just on that side of the graph? So the left-handed limit as f of x, as x approaches a specific number, they're going to tell you that number right here with this x and the arrow and a. A here is the number that they want x to move towards. And so as x is approaching that, this is the notation they're going to give you. The number where f of x is moving towards, remember f of x is just y. As you get closer and closer to that x value, what is y doing? And that is strictly the left-handed side that they are talking about here. So then the opposite is our right-handed limit. Our right-handed limit is what happens. Again, they're going to give you this x moving towards some number a, but now we're going from the positive side of the graph. So if we were to go all the way to the positive side of our number line and move towards that a value from the right, not to the right, but from the right, what is my y value doing here? So let's look at this example. We have this function here, some function given here with this graph. And they have told us, here is my value of x. They want to know what's happening from the left and the right, and they're going to denote it with this little minus sign right here for this, and this plus sign right here for that one. So this minus sign is going to indicate a left-handed limit. So when you see the minus sign, that minus sign indicates that you are coming from the left side of the graph. So this is the left-hand limit. And when you see the plus sign, that is the right-hand limit. That is not the direction that you're moving, that's the direction you're coming from. So what I like to do is I like to highlight on my graph what x value they're talking about. In this case, the x value is a. And then I am coming from the left side. So over here is the left side, and I am moving towards a with my x values. Well, as I move towards a with my x values, what is y doing? Well, y is approaching this number right here. That is my left-handed limit. Then we're going to look at it from the right side. If I'm right side, I'm going to start way over here on the right and move towards my a value. What happens when I do that? As I move towards my a value, what is y doing? Well, y is moving towards the same number in this case. It won't always be that way, but this is my limit. That's what I'm moving towards here. And that's what limit means. What is y doing as x is getting towards a number that they've told us to look for? So let's look at this. This is a piecewise function. Remember, we just did piecewise functions in the prior part of this particular section. So now they want us to look for an x value of 2. Well, the first thing I'm going to do is I'm going to go to 2 on my x-axis, and I'm going to highlight that value there. Now, the first thing we're going to look at is from the left side. That's what this little negative sign means. So from the left side, as I move towards that value of 2, what is my y value doing? Well, y value is moving towards this number, in this case, y value of 2. So that's why this limit is 2. As I go across this graph towards the x value of 2, my y value is moving towards 2. Let's look at then the right sided limit here. So now for this one, remember this is a right-handed limit here. That's what that plus sign means. And so I'm going to start over here on the positive and I'm going to move towards 2 from the right. Well, if I look at what my y value is doing as I move towards 2, my y value is headed to this number. Now you can see at that number, we have an open circle, but that does not matter. Limit is asking, what does it look like y is doing? Well, it looks like y is headed towards this value right here, which is a 3. And so the right-handed limit here is 3. Now, if I were to look at overall limit, if it didn't have a plus or a minus, they want to know what the whole graph is doing. Well, I can't answer that question because it's going towards two different things. And so in this case, I can only tell what y is doing from one or the other side, not overall. And that's where we get this definition of limit or overall limit, the limit of f of x as x approaches a. Remember, that's just saying as x is moving towards some number that they have told me, they're going to say, well, we're just going to use x to a. We're not going to have a plus or minus right here, just this value. Then they're looking for overall limit. Well, the only way you have an overall limit, remember this if and only if, the only way that happens is if from the left side and from the right side, you are going to the same number. So on that piecewise function, we did not have an overall limit or a limit without the plus or minus because from the left and the right, they were going to two different numbers. If they're going to two different numbers, you only have a left and a right limit. If they're going to the same number, you have an overall limit. So for this example, our limit from the left and our limit from the right was the same number. And so that is why we had an overall limit here. However, if you look at this second example that we did, we had a left limit. Well, the left limit was 2. We had a right limit. The right limit was 3. This, however, overall limit does not exist because these are two different numbers. Now let's look at 1, the number 1. If I look at what's happening as I approach the number 1, well, let's go to number 1. Let's highlight 1. From the left-hand side, it's approaching 1. From the right-hand side, it's approaching 1. This does have an overall limit. If I were to look at it right here, -1. From the left-hand side, -1 is approaching 1. From the right-hand side, -1 is approaching 1. This has an overall limit. So you can see you could have overall limits at specific points and then not at another point on the graph. There are three basic types of discontinuities that you're going to see. The first one is a jump discontinuity. And as the name indicates, you are traveling along, you jump over an area on the graph and you move on. This is typically a piecewise. You can see that this looks like a linear, this looks like maybe an inverted parabola. You also have infinite discontinuities. So for infinite discontinuities, you can see that you would have some type of vertical asymptote here and your graph gets infinitely close to it, goes to an infinity, in this case, negative here, positive here, and you can see that you have this potential vertical asymptote. And so when you have those, you will have what's called an infinite discontinuity. And then the last type is a point discontinuity. These are removable discontinuities. They cause a hole in the graph. Sometimes the function itself is completely undefined here. Other times the function is just defined somewhere else. So while there's still a hole, it is defined there, just not at the hole itself. And this is still a discontinuity. But you can see why it's called a point. It is literally one point in the graph that the function is discontinuous. And so when you talk about continuity, you could have a graph that is continuous everywhere. Or they will often say, is it continuous at this specific point? And so when we look at whether or not something is continuous at the specific point, then the first thing we look at is if we plug that number into the function and we look at the limit of the function, those two should equal. So the number that the graph is approaching and the number that's it's actually at should be the same if this is continuous at a specific point. Then you also have continuity on an interval. So rather than just looking at one specific point, they're going to say, is it continuous over a specific interval? In this case, they gave us this step function, and they want to know, is it continuous from 1 to 2? Well, it's continuous from 1 to 2 as long as this is open, because there's no breaks from 1 to 2. Now, clearly, at 2, there's a break and it jumps, and then it's continuous from 2 to 3. It jumps, it's continuous from 3 to 4. So definitely not continuous across the entire graph. Point, if it was a point within here, it would be continuous, but this is continuous over an interval. So for these, I want you to take a minute and see if you can figure out if these particular functions are continuous. If you don't think they're continuous, try to figure out where they're discontinuous and what type. So go ahead and pause the video, take a few minutes to look at these different functions and see if you can figure out some discontinuities in them. So this first one is a piecewise function. To figure out if this is continuous, we want to look at the places where they have defined it. So they've defined this particular function when it does not equal 2 and when it does equal 2. So if we plug in a 2 to these function pieces, as long as they equal, then that means that it's going to be continuous. So if I were to plug it in here, 1 plus 2 over 2 equals 1 plus 1 equals 2. Here it's saying when it does not equal 2, you can plug it in. So as I get towards 2, it's going to be there. So we're just going to see what happens at 2. Well, at 2, this part of it equals positive 2. Well, if it does equal 2, it's saying it should equal negative 2. These are not the same. These are discontinuous, and it's discontinuous at this value where it changes. It jumps. Let's look at this next one. Clearly, I have a potential problem in my graph. Anytime you see a denominator, your brain should immediately think, I have a potential problem in that denominator. And so what I can do is I can reduce it, right? We can take an x out. I still have a problem. I didn't get rid of my problem at all. And so remember, when you cannot get rid of your problem, this is a non-removable. Anytime it's non-removable, this is going to be an infinite discontinuity. Let's look at this next one. This is a polynomial. We don't have a denominator. We don't have like a root that we need to check out possible negative problems. So we don't have a denominator where it can't be equal to 0. We don't have a radical where it can't be negative. This is strictly a polynomial. In fact, this is a parabola. You're going to have some sort of parabola. This is continuous. There is nothing that causes a problem. And so when you think about continuity, you should start relating it back to when we looked at domain. Are there any x values that cause a problem? Let's look at this last one. I have a denominator. My potential problems are, where does this equal 0? So what I'm going to do, and pay attention to this negative because he tricks a lot of people. I typically put that up with my numerator. I'm going to factor this denominator. So I'm going to take that x out. It's going to leave me with x minus 5. Now I have two discontinuities. I have this one. So when x equals 0, I have a problem. And I have this one. When x equals 5, I have a problem. However, 1 is removable. So this is removable. If it's removable, I could cancel it out. That is point. If it is non-removable, I cannot cancel it out. It is infinite. And those are the ways that you're going to find whether or not there's a discontinuity and what type it is.